Okay, so in order to figure out what the molecular structure is, the first thing that we're going to do is we're going to figure out what the degrees of unsaturation. So when we talk about the degrees of unsaturation, we have to talk about the saturated molecule. The saturated molecule is going to have a molecular formula of CnH2n plus 2. So if you know you have 6 carbons, N becomes 6, and so in this particular case, it would be C6H2 times 6 plus 2, which should be equal to C6H14. Now what we want to figure out is how many hydrogens are missing in our particular molecule. So we subtract C6H14 minus C6H10, and we get 4 hydrogens difference. If we divide that by 2, we get our degrees of unsaturation, which is going to be 2. And this 2 now can be either equal to a pi bond and a ring, 2 pi bonds, or 2 rings. Once you figure out your degrees of unsaturation, your next piece of data to look at is IR, which you can tell by looking at the units here. These wave numbers tell you the frequencies. What you want to be doing is looking from 500 to around 4,000 inverse centimeters, and all we're looking for is functional groups. That's it. I know there's always peaks up here around 3,000, 2,700. You don't want to confuse these for functional groups. Functional groups like alcohols and amines and carboxylic acids are going to be a little bit further over to the left, whereas your carbonyls are going to be over here around the 1,500 to 1,800 mark. So these represent carbon-hydrogen frequencies, not functional groups. This peak here at 1692 represents an alkene. So what that means is this takes up one of our pi bonds and 1 unit of unsaturation. And if we look at our IR, we don't see any other functional groups that has a pi bond. We don't see any alkynes, we don't see any other alkenes. And so what this suggests is that we have a pi bond plus a ring. Okay. Next thing I like to do is I like to go look at my proton NMR. When I look at proton NMR, what I see here are 3 unique types of hydrogen. And these here in particular stand out to me. These must be on the alkene, because you see their parts per million come in between 4 and 6, and that means that they're going to be on the alkene. The other thing that I can pick out from this particular piece of data is that there are no methyl groups, which means there's no CH3s. How do I know that? Well, this has to be representing 2 hydrogens, the area under the curve. These have to each be representing 4 hydrogens, which gives me the hint that there's some symmetry, because we don't have methane around CH4. So this is probably 2 CH2s that are in the same environment, and this is probably 2 CH2s that are in the same environment as well. That's about all I can get from my proton NMR at this point. Now what I'm going to do is I'm going to go to my carbon NMR. And this carbon peak here, this is from the solvent. This is from CdCl3. And what I see in my carbon NMR is very similar to what I saw in my proton NMR. 3 unique carbons. This carbon here, that's the most downfield, has to be part of an alkene. These carbons at 25 and 22 aren't next to any halogens, we don't have any, aren't next to any oxygens, we don't have any, so they're very far upfield relative to the sp2 hybridized alkene. Now if you think about this, we have 3 unique carbons, and we have 6 carbons that we need to account for, and we have 3 unique types of hydrogens, and we have 10 hydrogens that we need to account for. So this signifies some amount of symmetry. And what we could think about are 2 structures. Oh, I should mention the mass spec. This here is our molecular ion. And this here is our base peak. Not the same. Base peak is going to be the highest peak. The molecular ion is going to give you your molecular weight. So this is the radical cation. Based on all of this data, we can come up with a couple of structures. We know we have a pi bond and we know we have a ring. So when we think about this, I always say the largest ring you can have in this particular case, because we have 6 carbons, is a 6-carbon ring. You couldn't have a 7-carbon ring because we don't have 7 carbons. And if we do this and put an alkene in here, we've taken care of 1 unit of unsaturation with the ring, 1 unit of unsaturation with the carbon-carbon double bond. We could also think of drawing a smaller ring and have some substituent hanging off. So we could draw we could draw 1, 2, 3, 4, 5 carbons, and we could have an alkene hanging off. Or we could draw a 5-carbon molecule with a methyl group. So what we need to figure out is which of these structures could be represented by this data. Now we could draw more and more options with smaller ring sizes, but if we start here, we might get an idea that we don't need to go any smaller. So let's start by looking at this group here, this molecule. What we see is unique number of carbons. We have carbon A here, carbon A here, carbon B, carbon B, carbon C, carbon D. 1, 2, 3, 4 unique types of carbon. We should see 4 signals in the NMR, carbon NMR, and we don't, so we can immediately eliminate this. Here we could have carbon A, carbon B, carbon C, and carbon D. Oops. And carbon D here as well. If we did this molecule, we should see 1, 2, 3, 4. Again, immediately eliminate. Now, if we look here, we can have carbon A, carbon B, carbon C, 3 unique carbons, same unique carbons that we see over here. And we have 3 different types of protons. The hydrogen's attached to the alkene, the hydrogen's attached to this carbon B, and the hydrogen's attached to this carbon C. So in the end, our structure should look like this.